All right, folks, good morning. Let's do this. Welcome to Friday. Welcome to Friday of week 11 for Physics 1300. Thank you all very much for being here so bright and early. Always much appreciated. We're going to finish up some nuclear physics today and talk about a few other things as follows. So quiz 10 starts Monday morning. We already had an announcement on this. A couple of people have talked to me about it. 4 attempts, 4 days. Spread them out, do some practice. This is on study guide 9, which is all about sound intensity, what do you call it, decibels, intensity levels. And it starts with the waveforms in the boxes, right? The open ends, the closed ends, what resonances can fit, resonances and harmonics and all that kind of thing. It's not bad. I promise you it's not bad. There's nothing on there that you haven't seen in class. So give it a shot on Monday. Hopefully you walk away with an 8 out of 8 and then everybody's happy. If not, do a little more studying, a little more practice, and get your attention. Okay, can you all still hear me? Let's just hope we're still recording here. Sorry, let me just check that. All right. So, do your 4 attempts. Don't do less than 4 unless you get an 8 out of 8. If you get an 8 out of 8, walk away. There's nothing new to see there on a different try once you get it perfect. But please do them all, folks. Go for that 8 out of 8. It helps your quiz mark immensely, as you know. I'm still going to do office hours next week, Monday, Wednesday, Friday, 11:40 to 1:15 or so. So once week 12 finishes, it finishes on December the 2nd or whatever that is, 3rd, I think. And your exam is on the 9th, which is the following Thursday. So the beginning of that week, we'll have special TA sessions, and I certainly will have a little Zoom help session, 1 or 2. I think Mahar will do the same. I'm back working at that point, so it'll be the evening for me. The TA ones will be through the day, so there'll be pretty good coverage on the day, Monday, Tuesday, Wednesday, and probably Thursday morning. I would think they'll have the TAs ready on a Zoom session for like panic last-minute questions. Don't have panic last-minute questions, please, folks. But if you do, if that's the way it goes, then should be able to get some answers. But I'll post what those are next week. Next week will be the exam structure and format. You're going to know how many questions are on there. You're going to know how it's going to be presented. I think I've already told you it's all multiple choice because you can't mark 800 not multiple choice exams very easily. It'll be on a Scantron card, which if you haven't seen one of those, I'm going to post next week what that looks like and how you fill it out and stuff. It's very, very simple. And once you've done it once, you'll be able to do it for the rest of your university career quite happily. But the first time, people kind of get a little bit confused, so I'll post about that. You're going to be doing your exam with pencil and paper in a room. You're not bringing your computer into a room. This is a question I've had a couple of times. It's pencil and paper, calculator, all that kind of stuff. So again, we will post on all of that next week, including how many questions. I am not going to tell you that there are 3 forces questions and 2 circuit questions and so on and so forth. It covers the whole course in about the proportion of time you spent on the stuff in the course. So go with that. We'll finish study guide today, study guide 10 today. We'll do some review next week, as I said. You have a review problem. It's in the week 12 lecture notes folder, and I'll repost an announcement about it today. Monday, we'll do questions 1 to 15. Wednesday, we'll do 16 to 30. Friday, we'll do 31 to 45, and then we'll be done. Come to class having tried them, if at all possible, because that is the best way that they can help you. But the lectures are optional, right? You don't have to be here next week. There's no new material. You're not going to drop a surprise exam thing on you next week. Anything that, I'll still tape the lectures. You'll see the lecture if you want to. But it is up to you. Or, if you want, come to whichever lecture you like. If you like the 1:30 lecture better, come on there. It's not that full. And I don't think there's going to be that many people here next week. So do as you will next week. Whatever is the best for you studying wise, please do that. And so instructor evaluations are open. You've received an invitation to fill it out. I think it comes through CourseLink. I appreciate a bunch of people who've done that. Again, if you do that, I can't see that you've done that. I can see that you've done that. I can see that someone has. I can see that 33 someones have, but I don't know who they are, and I certainly don't know what they've said. I find that out once the course finishes and you have your mark and you walk away and we never see each other again, unless we do. Please do fill that out. Please fill it out with the knowledge that whatever you say in there can't affect what happens in this course. Not that I would do that anyway. And I think it's only fair that if we ask you to go to your way to do this, that we give you some class time to do it in. So if you want to take like 5 minutes now and do that, please feel free. You got a question? Where is the exam? It is in 5 different rooms, and they are posted on WebAdvisor. So the exam schedule is posted on WebAdvisor. You'll be separated by room according, I think, to your last name. Question? No. Good. Okay. If you haven't filled it out and you want to, please go ahead. We'll take 5 minutes. I'll probably check in like 3 or 4 minutes to see if people still want time. And then we will carry on with the rest of the lecture. So proceed. And if people do have questions also, they can ask me them now. Does anyone not know how to find this evaluation thing? Great. Here today, finished, as enjoyable as it is. So I think I'm still recording. I think I'm gonna be able to post this. Who can say with this tech? As long as it doesn't cut it again, we'll be fine. All right, so we've been through nuclear decays. We've been through half-lives, which are the means by which we characterize nuclear decays and how much is left. We've been through some applications like carbon dating. We talked about activity, which is the rate of decay. And now we're going to get into what we started on Wednesday, which is attenuation, which is this idea that you can fire these particles into the human body, and they will go a certain distance, and you can understand how that works, and you can fine tune it. And so we talked a little bit about what matters when you're firing a particle, alpha particle, beta particle, into the body. Alpha and beta particles do not penetrate very deeply. They're charged, and so they interact too much with the atoms in your skin. Beta particles go a little bit deeper because they're smaller. Alpha particles are huge, and so they barely even get into your skin at all. But gamma radiation and other forms of electromagnetic radiation, it's all just light, right? Gamma rays, X-rays, visible light, ultraviolet light, it's all just different wavelengths of light. And so gamma rays are very high energy light. They're able to penetrate very well to a certain average distance and then deposit that energy in your body. And if you get billions upon billions upon billions of them from a cobalt-60 source bombarding your body and depositing their energy, eventually it's going to burn you, and even more eventually it's going to kill you. So we talked about that gamma rays are attenuated, which just means stopped, in the form of a decaying exponential, right? We've seen these curves before. We see these curves every time we have a decaying exponential equation based on how much energy they had to start with, where they penetrate less deeply if they enter with less energy, which I think makes sense. And depending on what they're going through, they penetrate less deeply if it's a more dense substance, which again, I think makes quite a bit of sense. And that's the 2 factors that we consider. And it turns out that the distance that they go is described by, yep, our old friend, the decaying exponential, as we said, and that the number of gamma rays that are still traveling through at a certain depth, which we would call the number at a depth, or n of x, turns out to be the number that was there at the start times e to the negative mu x. We're not talking about lambda t now, we're talking about mu x. X is our variable, we're talking about distance now, not time. And we have our attenuation coefficient, which is mu, which behaves exactly as lambda did. It's what changes based on energy and substance that allows that decaying exponential to take its form. So attenuation coefficient, as we can guess, now is not in units per second per day. It's in units per centimeter, per millimeter, per meter. It depends on the energy of the X-ray and the material that it's going through, as we said. And it just goes into defining what that attenuation coefficient is. And it behaves exactly the same way as all these other decaying exponential stuff we've done this week. And so the attenuation coefficient tells us how easily a particular material will absorb gamma rays at a specific energy. What you'll find in a question about this is we'll say gamma rays at 3 mega electron volts. That's not something you need to do anything with. All it says is we've defined a certain set of gamma rays. If you have a bunch of different energies, you have a bunch of different attenuation coefficients, and you don't really work with that so easily. So we say there's just one. Or you can recall that we took the half-life, we took the attenuation coefficient for materials radioactive decay, and we said 1 over it, or ln of 2 over it, because that's how that equation worked, was the half-life, right? And that was a number we could work with. What is the time it takes for half of these things to disappear based on this attenuation coefficient? Well, now 1 over mu, 1 over this attenuation coefficient, is the mean free path. What's the typical average distance that these things will travel in this particular medium with this particular energy before they interact or are attenuated? In other words, 1 over mu is the average distance or depth. And that comes out in meters or centimeters because mu is in per meter or per centimeter. And so if I say we've got cesium-137, it emits gamma rays, they have an energy of 662 kiloelectron volts, the attenuation coefficient for this tissue at this energy. So again, this energy and whatever tissue it's going through, the attenuation coefficient is defined for that. 0.0905 per centimeter. What is the typical distance a cesium gamma ray will travel before it interacts? We just said that the typical distance is this mean free path, which is 1 over the attenuation coefficient. So if the attenuation coefficient is 0.905, the mean free path, or 1 over mu is all that means. 1 over 0.0905, and we get 11.0 centimeters. So for these gamma rays in this particular tissue, the average distance they'll travel is 11 centimeters. And then we say, what's the thickness of tissue that results in half the gamma rays getting through? This is a significant number in this field of study. They call it the half value layer. What's the depth where you can predict that only half of them will be there after that? Kind of like a half-life, right? Mean value layer, half value layer. And so we just said that we still have a decaying exponential and we know how to work with those. The number remaining at a certain depth is the initial number controlled by this decaying exponential, negative mu times x. And if 50% of them are left, we're going to do that thing that we always do where we say the number at that depth over the original number is 50%. Equals e to the negative mu x. And so then we're going to say that the natural log of 0.5, this is all exactly the same thing as we've done before, is negative 0.905x. Didn't really use a lot of leave a lot of space around here to write here. You know what, I'm just going to write that a little bigger. The ln of 0.5 is 0.0905x, just working with the algebra of this equation here. And when you solve for x, you get 7.66 centimeters. So on average, a gamma ray penetrates to 11 centimeters. The half value layer, or this layer that typically results in only half of them getting through to that is 7.66 centimeters. So they all enter at 7.66, only half of them made it that far. And at 11, on average, they're done. That's it. The algebra here is exactly the same as the number of atoms remaining after decay, the activity after a certain time, the carbon dating ratio. It's all the same. It's all the same algebra. The only difference here is we're using a different decay coefficient, but it's just a different letter, right? It behaves exactly the same. So how much aluminum is required to reduce the number of 200 kiloelectron volt gamma rays to 10% of the incident value? And we say the half value layer for these gamma rays in aluminum is 2.14 centimeters. We haven't told you the decay coefficient. You need to know the decay coefficient to find how deep these things can penetrate, but we have told you the half value layer. So this is just a couple of iterations of the same calculation. What do we have? We want to know half value layer is 2.14 centimeters. What does it mean? It's the depth at which half of the original incident gamma rays are remaining. So that means that half, or 50%, are remaining. E to the negative, we don't know mu yet, but we know that the half value layer is 2.14. So what I'm saying is half of them are remaining at a depth of 0.214. And I can use that to find out for myself what the decay coefficient is, what the attenuation coefficient is here. And I so do in the following way. The natural log of 0.5 is negative mu times 2.14. And if I solve, that's a negative mu. And if I solve for mu, I get 0.324 per centimeter. Now I understand everything about how these things travel because I know their decay coefficient. I can plot that curve. Or I can specifically ask, how many are left? How deep is it that 10% of the original are left? What's that depth where we would predict that 10% of the original gamma rays are still traveling into this body? And then I'm going to say n of x over n naught equals 0.1 because 0.1 is 10%. E to the negative mu, which I know, 0.324. How deep is that? That's our x. I'm going to say that the ln of 0.1 negative 0.324x. And I say x is 7.1 centimeters. So what did I do? I figured out the decay coefficient because I knew this particular depth was the half value layer, and half is 0.5, so I could say 50% there. And then I used that information, that mu I discovered, to figure out how many were left, or how deep into the skin 10% of them were left. Any questions on that? Questions on how I set the two different versions of that up? Why I did two different versions of it? Yeah. Oh, all I'm saying is that half of them are left, right? N of x is the number that are present at any given depth. N naught is how many were there at the beginning. And if half of them are left, then the number that are there over the original number is 0.5, 50%. That's all I'm saying. And it's the same thing we've done in many other questions when we were talking about how many atoms are left when these things are decaying, right? If 40% of them are left, then their N of T over N naught was 0.4. Same thing. 50% of them are still left traveling into the body, so I'm saying 50% here. Any other questions? All right. So some applications. What have we? This is X-ray imaging. The way that it works now, as with all things, now it is not controlled by what we see on an exposed film. It's controlled by a computer who gathers the data. It's not even an analog image anymore. It's a digital image now, and we can take it and we can play with it, and we have such sophisticated equipment that it would blow your mind. And so it's the late 1800s, and Wilhelm Röntgen, a German scientist, was working with electricity, which was a very exciting thing in the late 1800s to be working with. People were trying to understand how electricity worked. And so he had what, a Crookes tube, I can't remember, a vacuum tube where he had an anode and a cathode, and he's basically setting up these big arcs in this vacuum tube and just kind of seeing what happened, because scientifically you could just sort of do that. And he had a sample of phosphorus across the room, and he noticed that it was glowing, which was unexpected. And so he, being a scientist, figured out that something must be happening, because that's what scientists know. And so he shut his lab up and kept his apparatus up and spent the next few weeks studying this thing. And eventually, what he noticed was if he put his hand in between his apparatus and this phosphorus, it looked like he could see the bones in there. And so I guess then you do what any great late 1800s scientist does. You ask your wife to come in, and you ask her to hold her hand right in that same place while you hold a piece of radioactive sensitive film in front of it. And of course, what we result in is the first X-ray image. Frau Röntgen was the first person who ever saw the bones inside her living body. And while I'm sure her husband was very excited to have opened up this new realm of science, what she said is, "I have seen my death." So that's that. I'm sure she got over it, but yeah, no one had ever seen that before. So that's the first X-ray image right there. It is unsophisticated, it is blurry, but you know what? You can see the finger bones there. You could see if one was broken. That's how it worked. And what happened, of course, was that in exciting these anodes and cathodes, I think the electrons from the cathode, I can't remember how it went. The electrons from one bombarded the other, gave their energy to that particular element. When that particular element had an energy bombardment, it excited its electrons. You know, remember how this works. And then they fall back to their original path. And when they do so, they release an amount of energy depending on how much they were excited. And it so happened that that wavelength of electromagnetic energy was an X-ray. And so it was giving off X-rays throughout the room, probably not too healthy for anybody. But eventually, you know, so the X-rays hit the phosphorus and made that phosphoresce. And eventually he did this thing, and then eventually, you know, here we are. And it went on from there. Once that was discovered, people went kind of nuts and started playing with it in all different ways. And that was that. But that was the first. And it's all about this emission of electromagnetic light, X-rays instead of gamma rays in this case, but very similar in terms of principle. How does it work? Well, you're going to take X-rays or gamma rays. You're going to have an object. And let's say that the object is made of one material with a more dense material embedded in the middle. And then you put a film there. The ones that are going through the sort of less dense material will reach the film a lot more than the ones that are going through the dense material, because we have this equation. The number that get this far depends on the decay coefficient, and the decay coefficient for this material means that it stops a lot more than these ones do. So the regions with higher density, why is that staying? Why does it do that occasionally? The regions with higher density, can it stay there, are you? No. Yes. The regions with higher density reach the film a lot less than the regions with low density. So here we've got a bones in a shoe. This is another very early X-ray. The bone is dense, so those X-rays don't reach the film as much, so it's less exposed. The nails, which keep on the sole of the shoe, also don't reach it as much because they're metal. They attenuate those X-rays a lot more, and so they are black as well. But anywhere that's white, a lot of X-rays have reached and exposed that film, and so it's a lot lighter. So X-ray imaging, the greater the difference in density of the tissue, the greater the ability to determine anatomy in an X-ray image. So you can see we've got some pretty great abilities to do X-rays now, partly again because of this digital imaging processing, and partly because our methods have gotten more sophisticated. We can see a lot of amazing things inside the body, especially if you use things like a contrast agent. So you put something in your body that attenuates the X-rays better. And if you can put it in such that it stays in some tissue of your body and not others, you can control which tissues attenuate in which way and just get a really great contrast. You know, if you fired X-rays at someone's midsection, which that is, Originally you might not have seen that contrast very well, but you can get a contrast agent in there, and it ends up just cranking up that attenuation coefficient enough where you want it to be that you get great contrast. And then CT imaging, so CAT scan, series of X-rays from different angles, and then you can use a computer to collimate them, and you get a 3D image of the body. Pretty amazing stuff. You got to spend some time in the tube, but then you can kind of scan right up through a body. And if you've probably seen this sort of video in one place or another. This is a cross section of a person. There's their spleen, there's their liver, and their spine. We're looking kind of down into their body, or maybe up, I don't know. We got radiation therapy. This is a very intense X-ray beam used to kind of, as I said, attack tumors in the body, which you can do with great control because you can understand what the mean free path of these things is. You can understand how to control their depth and put them where you want them, not where you don't want them, which is in the tumor rather than the soft tissue of the body. And so what you want to do is you maximize the radiation in the tumor. So you've got someone's head here, and presumably this is a tumor in the head. You want to minimize how much radiation goes into the brain. I don't think I need to explain why that is. You want to maximize what comes in healthy tissue. And we've got the means to really control that depth very well. So for this particular, we shoot from this angle, and we crank our energy such that its attenuation coefficient means it stops right in the middle. And then we shift the machine, and we dial back the energy or dial up the energy. We fire from that way, and then we fire from that way. And you can see they're all crossing. Like, you can't see that because it's not the right color. We're all crossing in the middle right here, and on average depositing the energy right where it needs to be. And on average, what we're not doing is depositing energy in the parts of the brain we have to go through to get there. Non-invasive, and it works really, really well. So you're going to take a CAT scan to image where the tumor is in a 3D fashion. You're going to plan the treatment. You're going to say, okay, we're going to fire from these 46 different angles over this amount of time with this amount of energy on each one. We've got the calculation power to do that now. You're going to simulate it. You're going to make the molds and the shields that protect the parts of the body you don't want to harm, because again, in 3D printing, you can make these things very easily and customized to each patient. And then you deliver the radiation. And again, it's sophisticated enough to work very well. A multi-leaf collimator. So this is another way to get a 3D image of the body. You can see different things in that. And it lets you image, again, we've got this head with this tumor. This is about what we could do before, but with a multi-leaf collimator, again, you can make this extremely sophisticated plan. So presumably here, it's allowed you to make the plan where the red is where you're going to deposit energy and the green is where you're not. Here, this is about the best we could do without these sophisticated scanning techniques. We also have brachytherapy. This is, I think, what I alluded to. Remember, I asked the question, how would you deliver radiation to a tumor in the prostate, let's say? Well, you make these little tiny beta emitters with short range, and they're beta emitters because they're just radioactive things that emit beta plus or beta minus particles. They work really well in very, very radiation sensitive areas. And so you can embed them. So what we have, we have that red spirally thing is the image of a tumor, and you can embed them all around. So it's not super invasive. You're just embedding these little tiny, size of a pencil lead, right? And you spread them around the tumor, and they deliver beta radiation in a very, very small area, but they're surrounded the tumor, so they just kind of work inward on this thing. Works really well. And so a small aside, you're all here, so you're all presumably intending to be scientists at some point along the way. This is a story about scientific discovery. So Henri Becquerel, you remember Becquerel because it was his name that ended up being given to the units of activity, radioactive activity, playing around with uranium salts, discovered that they give off something or other. He didn't know what it was, but he discovered that there was something. His student was a guy named Pierre Curie, who, as probably you recognize, Marie Sklodowska-Curie. She's a very famous person. He maybe slightly less so. He was Dr. Becquerel's student, and Marie worked with him on his research and was a student in her own right. They discovered polonium and radium, and they made up the term radiation. So again, we're finding these more radioactive elements and giving some names and then kind of characterizing how they work. And so we have these people. Henri Becquerel, we have Marie and Pierre. Marie and Pierre had a daughter, Irène, who married Frédéric, and so they are Irène and Frédéric Joliot-Curie. They have a daughter, Hélène Langevin-Joliot. She is, I believe, retired now. She's still in France and worked for most of her career as both a scientist, a physicist, I think, and an advocate for women in science. Henri got the Nobel Prize for the discovery of radiation from uranium salts. Marie and Pierre each got a Nobel Prize for their work in radiation and defining radiation and working with radioactive elements. Irène and Frédéric, I believe, worked on, I think they were instrumental in like defining that alpha particles were helium nuclei, and yeah, you know what, I might be crossing up my stories here. Anyway, they worked in radiation, they worked in radioactive elements, you know, it runs in the family, I guess, and they both got a Nobel Prize. Hélène does not have a Nobel Prize as yet, as far as I know. And Henri, when he died, he died from unknown causes, but radiation burns were discovered all over his body. So it's a pretty fair bet that if the radiation didn't kill him, it sure didn't help. Pierre was hit by a cart crossing a road. And it's said that he had some radiation burn on his body as well. Marie certainly died of radiation exposure. She worked too long with inadequate shielding. Not only did radiation undeniably kill her, her notebooks are still too radioactive to even look at without shielding. You can't even open them without, you know, having lead in front of you to read them. They're in a vault in Paris. And both Irène and Frédéric died from cancer related to radiation exposure in their work. So this amazing cohort of people who discovered all sorts of incredible things that have changed our lives and were honored for it with the highest respect that the scientific community can give, also paid for it quite dearly. So science can be dangerous, I guess, is the moral here. Take your time, be safe when you're doing science, and you too might be like Hélène, who has done wonderful and important things in her life and yet lives on to enjoy more of it. But quite an incredible family and quite an incredible lineage of work that was done. And so we get to the most important part of Physics 1300. You're welcome, folks. It's done. Thank you very much for a semester's worth of attention. Thank you very much for the fist pumps. I like that. We're going to do a week of review next week, so we're not technically done, I guess, but nothing new to be said. Please do come on up and ask me some questions if you'd like. I'll be here for another few minutes.